Good morning, everyone.
Good
Thank you for
morning.
being here.
Good morning.
Okay. Give people one more minute to filter in. Sorry about the last minute announcement on this one for people on the Waldron Left Slack, and thank you to Marcel for volunteering to present again. I don't want the burden to keep falling to you, Marcel, though, since you've presented. This will be your fourth presentation. So I'm going to volunteer for next week. So I'm doing that right now, and I'm hoping others will step up as well.
So these chapters were pretty short, so I combined 2 chapters into today's presentation.
Okay. Well, thank you for doing that, and you can get started so you have enough time to present both. So again, welcome everyone. Thank you all for being here. I'm sure more people will filter in over time as usual. And Marcel will be presenting 2 chapters today, function factories, which are functions that make other functions, which I didn't even know was a thing you could do, so I'm excited to learn more about it, and function operators, which are functions that return a function as an output. So I'm very interested to learn more about both of these things. So take it away, Marcel.
All right, thanks. Yeah, so I think these chapter 10 and 11 are pretty short, so I'll try to cover, just give you an overview of what these concepts are. And function factory, like Chloe said, it's a function that makes functions. So in this example, the only thing that varies is the input here. So you have a function, right, as that encloses another function, which is the output. And because this is the last thing that gets evaluated in that function, you get a function returned. And so this will take an EXP or an exponentiation, a number for which you will exponentiate x. And you can see how that would work, right? Power 1, 2 would give you a function that you can call square. So square and cube are functions. And there are some instances where you have data and you want to generate a list of functions from that data. And that's where this technique I think is most useful. So these are what Hadley calls manufactured functions, right? So you can start to use it. Once you create the function, you can start to add your x values or input some x values and you get a 9, right? So 3 squared is 9. And then 3 cubed is 27. So you can see how those are working. So so just to review, we covered first class functions and how you would bind them, just like any whenever you're creating a function, you would use the arrow to tell R that this is an object that should be kept or stored in memory. And then we have learned the concept of enclosures. So when you're creating a function, it takes that environment in which it was created and sort of keeps it or defines it. And then you have the function creates a new execution environment every time it's run. So remember that if we're just looking at the first class functions, you run the function, uses the environment, and then that environment disappears, right? It's ephemeral. But in this case, because we have some sort of nested function, that environment is kept within the enclosed environment. So there are multiple. Once you start nesting things, it becomes a little bit more tricky. So we'll see what that looks like. So Hadley says that of the three main functional programming tools, functionals, which are functionals, function factories, and function operators, I think they're the least used. And yeah, I would agree because I don't really use function factories, but there are instances where those are pretty handy, especially if you're graphing or using some statistical functions. So they don't generally reduce overall code complexity, but make it easier to create these digestible chunks. So so let's look at the outline for the chapter. We have how the function factories work, and how they can be used to implement a memory for functions by enclosing those environments. So you can allow data to persist across calls. And then we also have some examples from ggplot2, some statistical examples, and then it'll show you how to combine function factories and functionals to generate a family of functions. So these are some of the prereqs, and then we'll look at the first example for the factory fundamentals. So the key idea here is that the enclosing environment of the manufactured function is an execution environment of the function factory. So yeah, it's hard to understand this, and it takes a little bit more work to understand what that means. So let's take a look at the example here, and we can start by looking at the manufactured functions that we created in the example earlier, square and cube. So you can see that if you print those out, you'll see that there's an environment associated with those functions, as with any function, right? And then cube, same thing. You have an environment that was that comes with the function. So we know where x comes from, right? Because that's the input for our function, but we don't necessarily know what where exp is coming from, right? So if we use the Erlang mprint function, environment print, we can see more or less where that exp comes from. And it was actually generated when we called power1, right? We gave power1 an input, and that was the exp that was assigned for that environment. So even though these two look the same, exp, they could be different values depending within their respective environment. So you can use mprint and some other helper functions in Erlang to take a look at what those values are, right? So power1 with the 2 as an input, right, was assigning exp to 2. So you can see if you extract that value from the environment, you get a 2. For the cube, you get a 3, right? So that's why these would behave differently, because the data stored in those environments is actually different, right? That's the data that is varying. For example, we have a data set of numbers that we want to use to create a set of functions. So that's one way to store the data in that environment so that it's used by during the when the function is run. So we can see a diagram here of what that looks like. It's a little bit complicated, but we can see that square and cube have these separate environments and separate values for the EXP variable. And there are ways to redraw that as well. So if we use the function square 10 squared, and we get 100, right? So you can, so this is just saying that x is a different value and compute that, run the expression within that environment, and that expression is this x caret exp. So there might be some issues here that we should be aware of when creating these function factories, and one of them is you want to ensure that you force evaluation, and because there could be a subtle bug here. So to show you an example, we set x to 2, and then we run the power1 function with a 2 input, right? So then that returns a function, right? But it doesn't really evaluate the function, right? It just creates a function that we can use. And then if we set x to 3, what would you expect square 2 to return, right? So in this case, it returns 8 because the square function is looking for that x at execution time. So it's going to find the last value of x and give you some weird result. All right, so that's why the 8 is showing there. So because of lazy evaluation. So you can fix this problem by always forcing your inputs to be evaluated so that those are part of the environment when the function was created. So in this case, we add force exp for our argument, and once you create the square function, it will take that input, evaluate it, so it'll say this is 2 at the time that you created square, and then keep that in the enclosing environment, so that when even if the value of x changes outside of the function, it'll still have 2 because we forced the evaluation of the input when it was created.
Marcel, can I ask you a question? As someone who has, I feel like you are someone who's written a lot of functions. Have you ever done this force? Have you used it?
I've used it with other functions, like functions that take in an expression, like filter functions. So yeah, I've used it, but not in this type of context of creating manufactured function.
Okay, that makes sense. Thank you.
So whenever you create a function factory, make sure every argument is evaluated. So in this case, this simple example, we only have one input. So that's all we need to do for the EXP. And then we have stateful functions. So it allow you to maintain a state across function invocations. So that's sometimes useful if you want to sort of, for example, a simple example is to count things. And there are 2 things that make this possible. So an enclosing environment, something that stores our data. So that makes it possible. And then we have a special assignment operator with the double arrow, which modifies bindings in the enclosing environment. right? We can also use the function called assign. That also would help us do the same thing, but I think the double arrow is probably easier to use than to learn the assign function, I guess. So the assignment operator with the single head, I guess, would create the binding in the current environment. The super assignment operator rebinds an existing name found in a parent environment. So let's look at the example just so that you can make sense of that. We have a counter function, right, where our initial value is 0. And then we have a function, a function that will manufacture, and that function will take the initial value, add 1 to it, and then replace I with that value. So this double arrow is pretty much saying that we're replacing the I up in the parent environment. So the super assignment will change that value. So you can see how if you rerun the function if you run the function more than once, you'll start to add a 1 at every time you call that function. So for counter 1, the first time you run it, 0 plus 1 is 1, right? And then next time you run it, I becomes 1, and then it'll add 1 to 1 and give you a 2, right? Counter 2 was created once, so the first time you run it, it just gives you a 1, right? So these are different environments, right? Even though we use the same function that generates another function, right? So these are separate environments. So as you can see that in the pictures. So these are best used in moderation, and sometimes the environments can be pretty big, and you might not want to be able to manage all of that because the environments get saved, right? So they persist. And here we'll talk about some garbage collection. So for most functions that are ephemeral, right, you can rely on the garbage collector to clean up any temporary objects that were created inside a function. Yeah.
Have you ever used the super assignment operator in code?
Yeah, I have. But not really in this context. It was something, yeah, where you need to assign in the environment above where you're running your computation. Yeah.
What's an example, like when you would want to do that?
I think we have an example in BIOC Manager. Can't remember the exact use case, but yeah, I don't use it very often, so yeah. But it does come in handy when you're working with several enclosing environments.
Thanks.
Yeah. So because we have multiple enclosing environments, you might, as I said earlier, you might have some data that starts to become stale, or you may not need after for whatever series of computations you're running. So you can explicitly unbind any large objects with rm, and that will only keep the things that you need. So in this example, F1, we're getting a series of uniform random numbers from the uniform distribution and taking the mean of those numbers, right? And then providing a function output with the value m. So as you can see in our first call here, we have million, and we set this to G1, and then we look at the object size, so that will compute how big is G1, including all of its enclosing environments, and you can see it's pretty substantial because it generated 1 million values and took the mean of those values, but those values are still in the environments. So if you were to rewrite this function, because we're only taking the mean and interested in the mean, right? So you can remove the x vector with RMX and still have the same output, right? The same procedure. But now if you look at the size of the object after removing x, then you can see a reduction in size. So that's one way to sort of manage the objects in that enclosing environment so that they're not too they don't get too bloated. I'll skip through the exercises and look at some graphical factories. And so the example here is just using ggplot2, and you'll see that a lot of plotting packages use these kind of factories that take in a function input. And here's an example from ggplot2, and it uses the scales package to make it easy to customize the labels. And there are some formatter functions that make it easier to control the appearance of the axis breaks. So it may look a little bit weird if you're just using them by themselves, right? Comma format takes a vector. So comma format outputs a function. Then you can call the output function by just opening and closing the parentheses and providing an input. So it'll add a comma to your values. And then here you can replace any thousands with the K, right? So you have 12K in the first instance and so on. So you can see this in action when you're using the scale Y continuous function. You can provide a function to format the labels the way you want them to look. So you can use a comma format, number format, scientific format, and then you can see how that would look like when you plot.
That's cool.
Yeah. So it gives you a bit more, I guess, customization of what inputs you can provide to each of those functions, as long as they have a sort of consistent function output. And then for histogram bins, same thing. You can provide some functions accept a function as an input for like the bin width. So in this example, the bin width is a constant. And but you can provide a function here where he shows that you have a function factory that takes an input, and you force the argument, force evaluate, and then max, and then that it takes n and uses that as the denominator for this max minus min operation. So instead of having a constant, you can have bin widths by 20, and it will give you something that you can apply to each of those facets that you're plotting. So instead of, because some data might be larger than others, so I think this would allow the bin width to vary across the facets, if I'm interpreting that correctly. Yeah, and then I'll go into the ggSave, which is another example where you can have some functionals or manufactured functions that will allow you to save a format. And one challenge here is that the base graphics devices have minor inconsistencies in their interfaces, so you have to work around that. But most have a file name as the first argument. Some are called file. And then width and height use pixels by default. In the raster graphics devices, use pixels by default, but for vector graphics, they use inches. So there are some differences in the default arguments, and probably for good reason. But here's what that function would look like. Say, for example, you want to create a function, plot dev, that's pretty generic, but works off the extension that you're trying to save. So whether it be like PDF, SVG, EPS, and a DPI value. So we force the DPI, and then we don't really need to force ext, because once you are inspecting ext, it's sort of like the quantum physics thing. But once you look at it, you observe a value, and then it gets evaluated. So by putting it in switch, it'll look at the value and see which one would be the corresponding function to use based on the extension. So so you can see that some of these calls are wrestling with the interfaces, like file name here needs to change to file, because PDF has a argument called file, but file name was the one that differed. So the point is that you'll get a function back, right? And then so plot dev PDF would give you a function, right? Plot dev PNG will give you a function for saving PNGs. And then we'll try to go over these statistical factories, and there are some examples: Box-Cox transformation, bootstrap resampling, MLE. So for Box-Cox, it's a type of power transformation used to transform data towards normality. So it has a single parameter, lambda, that controls the strength of the transformation. So you could express the transformation as a simple 2-argument function, right? Here we have x and lambda, and then you could have some checking of the lambda parameter. So make sure that the length of lambda is 1, and notice that we don't have a force function call here, because length actually, so once you inspect your input, it's sort of evaluating the input, right? So if you do length on lambda, then you don't need to force it anymore, right? That's why we don't use the force there. But and then we have some condition: if lambda is 0, take the log of x, otherwise do this. And then to reformulate this as a function factory, we have Box-Cox 2. So the first one was not a factory, right? It just was a simple function, but all of these arguments are lazily evaluated, right? So they're used they're lazy until they're inspected, so to speak. For Boxcox2, we have the function output, right? We have a function that takes in a value. If it's 0, it'll do the log of x. Otherwise, it'll provide this function, right? And then we'll see what that looks like. We can put that in a ggplot call with a set of values 5.5, 1, and 1.5, and it will get the value of those outputs, those functions, as a graph for all of those all the times that we ran the manufactured functions with those inputs. So you can see how that would look like. Same thing for if you're creating bootstraps. You have boot permute, takes in a data frame. You'll have var, which would it looks like some kind of column, df var, yeah, the columns that you would select, and then in the function it will take a sample of rows from those from that column. So you can say boot permute empty cars. It will take that data, the empty cars data frame, extract the MPG column, and give you a function that you can run, which will sample the values in the MPG column. So that is meant to be random, right? So if you run it multiple times, it'll give you a different set of values every time. One advantage here is that with a parametric bootstrap, where you have to first fit a model, you can use a function factory, and you can do the setup once, and then when the factory is called, you set it up once rather than every time you need to create a bootstrap. That's the point. So you write your function factory that takes an input as a data frame and a formula, which you want that to vary, right? So that formula becomes the formula for the LM function call. df corresponds to the data in the LM call, so you get a model, and then you can extract the fitted and residual values, remove the model, right? Because some of that fitted object might be pretty large, and you don't want that hanging around, so you can just remove it because you're only interested in looking at the fitted and the residuals. So that would give you a function factory that adds the fitted and a sample of the residuals. So you can see what that looks like. Your formula in this example is MPG and weight, and so you get those fitted plus residual values. So for MLE, I think it's more of the same thing. You just want to generate a function that you can use for several values. So I think I'll skip this part, but it's good reading over and understanding how you can use like something like optimize to find the value that you're trying to maximize. So here's an example where you can use function factories and functionals. And so you have a list of values. So this would be like your data as a list. So for square, you have 2, cube, 3, root, half, and so on, right? So you can use per map with the list to run power one for all of those. And that will create a funds object as a list that has functions, a list of functions. So you can say funds $root to call that function and provide an input 64 to get the root. So
This is some crazy stuff.
yeah, it's possible, but I think this starts to touch upon the R6 way of doing things, and probably would be the preferred way once you start working with a lot of functions. But yeah, this is something that you could do with data. Just take the data and generate a function from the data. And then he shows that you can use with, which is a handy function that will sort of throw you into the funds. Go ahead.
What is the take-home message of that funds $root output there, which looks like all of them would look like? Like it does, there's no hint in there that this is a square root function. The one below that where it's funds $root.
Here,
Yeah,
this is just printing the function.
right. But why did they show that? Because it looks to me, I mean, it looks exactly the same as every one of those manufactured functions would look. There's no square root in it.
Yeah, because that's what Power One is doing, right? It's creating an enclosed environment, so you can't really see what the value of EXP is, and unless you dig in and inspect the environment.
Right. I guess that's why they're showing this, just to show that you would have to inspect that environment to see what EXP is.
Yeah.
Okay.
Yeah, and some like the RAPI client package uses this type of way of creating functions from an API. So it takes all of the sections of the API and it creates a function for each endpoint. So you have a single object that provides a number of functions that you can use. So one downside is that you have to prefix everything with funds $, right? And in order to eliminate that syntax, you can use with, which allows you, sort of puts you in the funds. It takes everything inside of part of funds and think of it as moving it up a level. So you can just call root simply without the funds prefix. This also works for data frames, right? It's a list. So if you say with empty cars, MPG +1, it should add everything for MPG, add 1 to the MPG values. For a longer effect, attach is also possible, right? Since you have a list of functions, it's not too bad. And here he makes that note that you've been told to avoid attach. And that's generally good advice, but it's different because you're attaching a list of functions and not a data frame. So we always recommend against attach on a data frame because that's not recommended. puts all of the variables in your global environment, and then mayhem will ensue. So if you do it for this list of functions, then you can just detach whenever you're done if you want to sort of work with those functions without using the prefix. And then he mentions this Erlang triple bang, I think it's called, notation. So what it's saying here, it's take all of the functions inside of funds and move them to the global environment, and then you'll be able to use root, call root in the global environment, and then the reverse operation. So that's it for function factories. I'll quickly go over some function operators, and a function operator will take in one or more functions as input and return a function as an output. So previously, we were just working with some constants, some data in the example, but here you have a function that you can use to output another function. So here's an example called chatty. It takes a function input, you force the function, and then you create this function that will use the input and the arguments, provide a result, and then print something to the console with cat, and then return the result. So our function here is the square of the value, and chatty will take that function, operate on all of those values. Here we're using map double, so we're sort of taking all those values and running that chatty function for each of those values, and you'll see that it'll print to the console with cat every time for each of those values in that S vector. The function operators are closely related to function factories. They're just a function factory that takes a function as an input. So it's a small difference. Previously, we had some data like a vector numbers, and here we're using a function as the input. Like factories, there's nothing you can't do without them, but they often allow you to factor out complexity in order to make your code more readable and reusable. So in the outline here, we have two extremely useful existing function operators, and they'll show you how to use them to solve real problems. And then we have an example for downloading many web pages using the function operators. So in this case, for existing function operators, we have per safely and memoize, which is a pretty neat function. So you can capture errors with per safely. And this sort of reminds me of things that BIOC parallel does, right? You can have a list of values here that you want to operate on, right? And some of those maybe of a different type in this example, simple example, right? You have a character vector, and the others are valid numeric vectors. And if you run this with a for loop, that would it will error for the character vector, but all of the other ones would still be computed, right? So you can have a result, but you'll also get some NA because of the error. You're trying to sum on a character, if you're trying to run sum on a character vector. If you do the same thing with a functional, like map double X, which is our list, and run the sum on all of those. It'll stop at the error, right? So you don't get anything back.
Why do they call that a functional?
This is a functional because the sum is a function input.
Ah, I see.
Yeah, so it's running sum on every element.
And let me see again what the per safely was.
So yeah, per safely will keep running even if there is an error. So you wrap safely, you wrap sum with safely.
So why
So
is this a functional since it's still taking a function as an
it,
argument?
it is a functional, yeah. It's a functional.
Okay, but is it? Oh, okay. So we're talking about, right, two different functionals here, safely as opposed to map.
Yeah.
Got it. Okay.
So if you do safe sum on the first element of the list, it works okay. But if you do safe sum on the fourth, it gives you some error element that's populated. The first one was null. The one with the character will give you the error. So that reminds me of what BIOC parallel does. It sort of especially if you're running like parallel operations and big computations on different nodes or computers, you can you don't want all of it to fail, right? You only want whatever node failed to return the error. So it sort of reminds me of that. So you can use safely with a functional, right, and map that to X, and that will give you that list of outputs. So and the error. So just showing you how that would look like in when using it.
Huh.
So yeah,
I'm just learning things as we go. I didn't know about some of these features of per.
yeah, I didn't either. I was always using BIOC parallel. It's like, yeah, but it's interesting
Yeah.
how they reworked. Well, things are rethought of and reworked
It's
in
super convenient.
different
Geez.
contexts. Yeah,
I was just wondering too if they have parallelism built into it. I'm sure they
I'm
have
not.
some parallelizing solution.
Yeah, maybe. So, and then he says you can transpose the output to make it a little bit more easier to work with. Like maybe you want to only get all of the results, then you can just extract that part. Or you can look at all of the errors, so they're not interleaved, I guess, in the previous output. So makes it a little bit more convenient to work with. And then you can easily find the results that worked and the inputs that failed. So take the error part of the list, check to see if they're null. That will give you a logical vector. And you can sort of narrow down which ones were which one had the error and which ones were okay. So you can do that for many different situations. If you're fitting a GLM, there might be some issues with optimization. So if you try to fit all models and you're running that functional little error, right? If one of the models doesn't fit, but if you use safely, then you can only look at and inspect the ones that did not converge, for example. So it comes with three other function operators in a similar vein, possibly. returns a default value when there's an error. So so it's reserved for cases when there's some obvious sentinel value like missing. Correlate turns output messages and warnings into output message and warning components. So for inspection. And then auto browser automatically executes browser inside the function when there's an error. So that's pretty convenient. You can sort of look at what went wrong inside of that part of the computation. And then memwise, also another pretty good function to use if you want to save some time. Memwise means that the function memwising means the function will remember a previous input and return some cached results. So it's an example of the classic computer science trade-off of memory versus speed. So the memwise function will run much faster, but it will store all of the previous inputs and outputs, so it'll use more memory. And I think with computers having more memory, that might be a better way to do things, as long as we don't hit the limit on our local machines. But here's a toy function. So say we have a slow function where we have a consistent or an input, a consistent input, right? And in this case, it's 1. It'll sleep for a second, then do 1 times 10, run if 1, and provide the result. The next time you run it, because these things are ephemeral, right? It will take the same amount of time, right? To go through all of those steps. If you memorize it now, all you need to do is wrap it with memorize, and you can give it a new name, in this case fast function, and it will, first time you run it, right, it will take the time it needs to compute all of the results, but the next time you run it, it will see that your input hasn't changed and return the cached result. So it'll give you the same value. Sorry?
I'm learning so much stuff.
Oh yeah. Yeah,
Same.
it's pretty handy to use the memwise. Even though I don't use it a lot, it's nice. And here's an example with the Fibonacci series. We have the naive version of the Fibonacci would take Fib 10, Fib 9, Fib 8, and then compute all of those. So this is what the implementation would look like. But the point is here that if you do Fib 23 and then Fib 24, it's going to run all of those computations, right? But if you memorize the process, it will take a lot less time, right? Because you already went to 23. When you go to 24, it just needs to do 1 more. And then that's pretty much virtually no time.
Wow.
Took no time to figure out what the value was.
I wonder if it also solves the so-called tail recursion problem in R, that because of all of the promises, when you do recursive functions like that, it can take a huge amount of memory. I wonder if it solves that.
Well, this takes up more memory, right? Because it's caching all of the results somewhere.
Yeah, but the cached result in this case shouldn't be, well, I don't know. Yeah, I don't know, but one of the things I learned a long time ago is basically don't write any tail recursive functions in R because they're slow and memory intensive. But I don't know, maybe it's been solved.
Yeah.
Huh.
Well, so he does provide some warning for using memwise everywhere. Like if the function is not pure, so it might be that it's relying on some external inputs that are not part of the standard inputs. You might get a subtle bug for memwise results. So he figured that out the hard way in available packages. He tried to memwise that, and sometimes those available packages changes even if the inputs are the same. The output changes even if the inputs are the same. So I guess think carefully before memoizing a function. And then the case study here was that he was using Safely and Memwise to download a bunch of URLs. So it's simple with walk-to and file download. So you have a list of a vector of URLs, character vector with names, and you create a path to a temporary directory with the names of the files or the names of the URLs and an HTML extension. Then you take all of the URLs, download them, put them in the path, and we're using walk-to because we're not interested in the output. We're only interested in the side effect. And you might want to add a small delay between each request to avoid hammering the server. So you don't want to send too many requests to the server if you're looping through things, and the server might not be able to handle it. And then show a dot every time that the function, so that you know that the function is working and doing something. So these are features that you can add using a for loop, for example. So you can sleep for 1 second or 0.1 seconds and then add a dot for every iteration, every other, I think, iteration looks like, and then download the file. So it's suboptimal because it interleaves different concerns, pausing, showing progress, and downloading. So it makes the code harder to read, and it's better to write a function operator that adds a small delay. So you can create delay by with 2 inputs, f and amount, add this syslib function, and then use f as a function input that you will provide as part of the output. So you delay by, you can run it here, delay, I guess in this case, we're using $100 as the input to run if that's right. Right? Yeah, so run if you run it without the delay, it's pretty instant. But here you have a 0.1 second delay, so that is takes a little bit longer. So then you can start to add this to your walk-to, right? Delay by 0.1 seconds. And then you create another function to display the dot So it takes in a function and an n for those. You use your counter setup here to change the values of I, and for every other value, you add a dot here. So you can see dot at every 10, and that will produce a dot. So if you have 100, you're doing this 100 times, you should get like 10 dots here. So then you can express the original for loop as a walk2 dot every delay by. So this is a little bit hard to read, so he rewrites it using the pipes. So you download file dot every 10 delay by 0.1. So it's easier to read. And that's pretty much the function operator. So there's some when I'm working with these things, I probably would use some package that has that shows you the progress, so you don't have to really implement this yourself. But it's good to learn about these techniques.
Yeah, that was very fascinating. Does anyone have any questions for Marcel? We are kind of over time, so any quick questions?
So sorry, walk2 is just an implicit for loop.
You could think of it like that. Yeah, walk2 takes two parallel vectors, so that's the two part. And yeah, runs those functions for each of those elements in those vectors. But it's called walk because we don't care about the output. We're just, I guess, walking through the for the side effect.
It's about the journey, not the destination.
Yeah. Yeah, exactly.
Okay, well, thank you so much, Marcel, again for presenting multiple times in a row. I have signed up to present next week as we get into objects and object-oriented programming, because I feel like that's one of the things I'm weakest at is objects. So please come back next week. And once again, just big thank you to Marcel. Thank you so much for presenting today and last week and a few weeks ago as well. So thanks again. And please, if you are interested, please sign up on the GitHub page on the wiki, and have a nice weekend.
Thanks,
Thank you,
everyone.
Marcel.
Bye.